Okay, we got into 30. Good. So let's get started. So we're happy to start with Gregor, who's going to tell us about this Post-Minkowskian Framework and the Boundary-To-BoundDictionary. Go ahead, Gregor.
Yeah, thanks a lot. I would like to start by thanking the organizers for inviting me to talk here, and of course for organizing this whole conference over the last 3.5 weeks. So today I'm going to talk about the first series of papers here with Raphael and Cheng Wen, and then I was going to present a new result that we'll hopefully publish, where Christoph Tlapa joined us, who is a new postdoc that will join us here at DC actually at the end of the year. We already heard a lot of motivation over the last couple of weeks why we should do what we're doing. So I thought I can give you a little bit of a different motivation. So a few days ago, I was walking with my dog, and I saw that we have a small fan community of gravitational waves here in Hamburg. So I thought that's nice. And yeah, it's good that we have some local support here. Okay, so to become serious, I was asked to talk a little bit about this boundary-to-boundary relations that you've worked out. So essentially this part of the diagram where I describe all the relations between a lot of quantities. So at the heart of it is a relation that tells us that essentially we can compute quantities in the scattering regime. So if you just have two bodies scattering with a positive binding energy, and we can use this data to learn also about the bound case. So essentially what's relevant for gravitational wave observatories like LIGO, Virgo, and also future researches. Okay, we have some background noise here. Okay, good, thank you. So this will be the second part of my talk, where I focus on that. I will try to explain how this works, how we found it, and somehow you can understand it. Due to some new results that we obtained actually in the last week, I also decided to talk a little bit about our PM EFT construction. So this is all about how we can actually get the input data, let's say the scattering angle, or rather for us, and what we directly compute is this deflection, so the change of momentum that one of these word lines will take. So let's try to explain that, how we obtained all the results here. And then there's the newest result that we have, where we constructed the potential contributions to the scattering angle at 4 p.m. for point-like sources. We already also saw that there's a lot of relations between all these quantities here. So for example, it all started actually with this relation here between the scattering angle and the scattering amplitudes. I will not talk much about that, but I will give you some ideas of this Firsov formula, and that it can also be generalized for the newest results if you start including logs, and even hopefully then, well, at least for aligned spin, and then maybe in the future even for generic spin. We also heard Raphael talk in the conference where this idea of analytic continuation can be extended even to some observables for radiative effects. For example, here, the loss of energy or the loss of angular momentum, which is also related to this paper by Bini and Tamur that studied very similar relations. So at the end of the day, all these relations are somehow connected to each other. So it doesn't really matter if you compare the scattering angle and the periastron advance, or if we talk about radial actions in the hyperbolic case or elliptic case. In the end, it's all some of the underlying geometry, the continuation of these orbital elements that immediately gives you all of these relations. I'm not going to talk about PN methods, so I just put it here for completeness. Also there, of course, they can give us the same type of input. They compute one of these quantities, use all our identities to relate them. And hopefully, at least for conservative effects, this diagram here should be commutative. All right. Okay, I'm actually going to start off with the Post-Minkowskian EFT. We already heard quite a lot in Raphael's talk, and also some related stories the last 2 days. I will be very brief on our setup, as Raphael has described it, and focus a little bit on the new effects and some just interesting details that I think might be useful for the community here. So the generic idea is that we'll have a purely classical setup. So I'm going to just put my Einstein-Hilbert action, and I'm going to couple it to some point particle action. The general idea is that I start from this full action. I'm first going to compute the effective action, and from there I can then decide what I actually target at the end of the day. So this can be the deflection angle, the flux, the waveform, whatever you like. At the heart of it is this effective action. They compute once and can reuse it for whichever observable I'm interested in. Compared to other approaches, we are going to do a perturbative expansion in the coupling constant G, which is a nice feature in that sense, because we can use all the particle physics type and amplitudes toolbox. So let's say all the integration techniques. Also, of course, all the fast programs that can compute Feynman rules for you, tensor constructions, whatever you need. It's out there. There's amazing technology, and we're really able to use all of this to study this GR problem. Here I say yes, we can also include not only point particles, you can add several terms here, you can add spin, and in principle, you can do arbitrary n-bodies. I'm not saying here that it's easy to do n-body. We have seen this paper by Plevko et al., and it's not easy to do it. The integrals are getting very hard, but in principle, there is nothing to stop us from there once we are able to do these integrals. Okay, so in principle, it's all understood what we have to do. Also note here that I'm a little bit sloppy here, because in principle, this is just the action for the in-out formalism. If I really want to compute the true quantities, including dissipative effects and everything, so really the full complete scattering angle, let's say for point-like particles, I'm going to have to use this thing called informalism. So far, we haven't done that. Well, we have started it now in the last month or so. So what you do is that you have to double your fields. Essentially, you take your action from above, and you have to double your action. This minus sign here, so you will have two graviton fields, H1 and H2, as well as two word lines for each of your particles. So you're going to essentially have 4 word lines now. This might somewhat sound bad, because remember, we are doing Feynman rules. So the danger here is that it really explodes, but it's actually not as bad as it sounds, because you only have to keep these 4 fields until you do the equations of motions. And once you have computed your equations of motion, so your higher order correction of the word lines, you can then essentially set the difference of the 2 word lines to 0. And it's doable. And even more exactly, you can go to this Keldysh variable, which clean up the Feynman rules quite a bit. So it's not as bad as it actually sounds. It's still doable to quite high orders. Even better, actually, so maybe that's a comment here, that if you just care about the conservative 4 p.m. tail of the radiation reaction, you won't actually need the in-informalism. I'm going to tell you a little bit more in the end of this part, that actually the in-out integrand, if you start adding us this so-called self-energy diagrams, will be sufficient. The reason for that is that only ever, for tail effects, only ever 2 gravitons lines will go on shell, and the boundary conditions, i.e. zero prescription of the gravitons, will not matter as much. So this integrand we already have, and hopefully we will be able to finish this problem here very fast. So what I mean by that, I'm sure you've already seen this type of graphs. Those are the guys that go into our effective action. And if you don't care about the tail, we're also going to have this type of diagrams here. Of course, for us, we iterate, and once we have the effective action, we're going to iterate the equations of motions. That means, of course, you'll also somewhat connect this line here down once you iterate the equations of motion, let's say, of the second word line. We have optimized essentially this whole setup by optimizing the Feynman rules, plugging it in, writing efficient programs for it. And the integrand part here is really not the problem of the computation. At the end of the day, it all boils down if you're able to do the integrals or not. So today I'm going to focus on the deflection, so on the scattering angle at the end of the day. It's more or less equivalent. So what we're going to do is simply we make an ansatz for our word line. So I'm going to expand it. So I'm going to start from 2 incoming word lines that are with a distance, horizontal distance given by the impact parameter, that are coming in with velocities u1 and u2. And what I want to compute are these higher order corrections, these word line trajectories. How I'm going to do that is, well, I'm going to take my effective action in a post-Minkowskian expansion. I'm going to vary the action, and I can compute the corrections order by order. So the observable I'm going for is this DeltaP, which will appear all over again during my talk, which is, of course, simply obtained by varying my effective Lagrangians and integrating up over the whole time. Once you have it, it's then simple to get your scattering angle out of it. All right, so that's the general setup. Of course, now you have to do a lot of computations to actually get something out of it. The hard part is to really do these integrals. But before we get there, let me maybe exactly show you what is known until now. So up to 3 p.m., this was established 2 years ago by several groups by now. What we do, and what is nice to write down, is actually this chi-b coefficients. So I'm expanding my scattering angle around g over b, where b is my impact parameter, and I really target each of these coefficients here. They can, up to 3 p.m., they can be nicely written down as I show down here. So this is really just exactly maybe specify this is the result in the potential region only. There's no radiative effects, and there's not, so it essentially misses the radiative corrections here. So since last week, we also have the 4 p.m. Result in the potential region, which reproduces this result here by the group of Bernadal. So we checked that this DeltaP here that I'm showing you here reproduces their scattering angle. I've written here the result in terms of this variable x. This has some disadvantages and some advantages actually. So the nice thing is that you won't ever have any square roots in all of these expressions here. On the other hand, the polynomials or your rational guys here look a little bit more disgusting. It's the very same structure as they have found. So here I'm just showing you the part in the b mu direction. So in principle, you have 3 external vectors. You're going to have the impact parameter b, and orthogonal to it, you're going to have u1 and u2 from both sides. The u1 and u2 directions, first of all, do not matter if you want to compute the scattering angle, because they're exactly orthogonal lying on b. Either way, as long as you're looking to conservative quantities, they can also be bootstrapped simply by momentum conservation and on-shelfness of these guys. So the simplest contribution, which is actually a good cross-check if it works out, is this Schwarzschild limit here. So that's essentially the piece when you set the nu to 0, the symmetric mass ratio. We're going to have this artificial 1 over epsilon pole, which we're going to comment on later a little bit, why it's somehow annoying us and why it's there. And finally, we have the important part, the finite pieces, but also those actually contain some non-physical part exactly because of this pole here. Here the feature is exactly as you've already seen in some talks before. There's these elliptic functions k and d appearing, showing up here. And then we have a bunch of dialogues, and finally just logarithms of various arguments in x. So it's usually x plus 1, x and x squared plus 1, and maybe x squared. I'm not quite sure, something like that. Exactly. So there's nothing new here, and it exactly reproduces the result of Bernadal. What, of course, we're shooting for now is that we would like to complete the full PM scattering angle or the trajectory, whatever you want. So for that, there's one part that you hopefully can obtain very easily, which is, as I advertised before, this conservative part of the radiation reaction tail. For that, we will not need the full in integrand, but the in-out integral is completely sufficient. Furthermore, for that part, also we hope that it's going to be quite easy, because we do not expect to get any new integrals. At least we won't expect to get any hard new integrals. If you look at the PN expansion, which is already known up to some orders, you will see that the tail does not contain any pi to the 3 pieces. That means that there cannot be any elliptic functions in the tail, which at the same time means that those are the simple integrals. I will explain about this part about integrals a bit later, but the operator really is, as long as there's no elliptic, we can easily solve them to essentially any order in epsilon. The next step then would of course be to also include dissipative effects. For that, we really will need the integrand. The integrand itself is not that hard to obtain. We have essentially automated codes to do it, and we will hopefully spit out 4 PM very soon. The harder part there is to get the soft boundary conditions. And we already heard a few talks about that by Mao, Carlos, and Michael, for example. At 3 p.m., we start to understand the systematics. So for example, we can look at these two papers here, where I've started to compute the full soft boundary conditions. Since the structure of the integrals at 3 p.m. and 4 p.m. is very similar, it seems like the same techniques will also be applicable there. So really, once we figure that out, there's essentially not much stopping us from going on. There are though 2 points that's a little bit challenging. So one of them is that if we have an informalism, you're going to get retarded advanced propagators. If you compare to the amplitudes approach, or let's say the KMOC approach, instead of having advanced retarded propagators, they have cut integrals, but you also cut the graviton lines. In our formalism, we never cut any graviton lines at all. The only thing that we're going to get are advanced retarded propagators. But they come with a difficulty of their own, because, for example, they're breaking this nice symmetry here when you just swap the sign of the propagators. Okay. The symmetry is quite useful once you try to solve, once you find identities among all your integrals that you're going to get. And at the end of the day, it will just mean that you will have to compute more master integrals. It's also a little bit problematic because it's annoying that most of the tools actually completely give up if you try to find symmetries with advanced or retarded propagators. And that's why there's some rethinking and workarounds that we have to work on. A second point is that now these UA contributions that I didn't give you here, but that are actually there, yeah, I didn't give them, yes, cannot be bootstrapped anymore once you have dissipative effects. Momentum is not conserved anymore, so it's going to be more complicated. For us, that means we're simply going to get more integrals, but in principle, the whole method should still work out. So it's just going to be a little bit more work, but systematics still work out. All right. Are there any questions until now? Because if not, I will now go to a little bit more technical part and talk about integrals. All right. Very good. So for us, there is some crucial difference with respect to the amplitudes approach, because we immediately land on a very small set and a very well-defined set of integrals. We essentially already know the structure of our integrals to all loop orders, including potential and radiation parts. So everything is there in this type of integrals. So what we have here is, let's say, Feynman integrals, where for each loop momentum, we have one cut linear propagator. Those are these delta functions here. These L's are dotted into the velocity, so either here it's U1 or U2. You only have 2 lines. And of course, correspondingly, the one that you don't have upstairs, you might in principle have downstairs as a usual linear propagator. The only thing that is also added here is that we have different families of squared propagators. These guys only contain L's and Q's. So it's nice here that we do not need to do any small Q expansion or do any expansion of any kind to land on the soft integral. They are really manifested there in our framework. Also, there's no quantum contributions ever. Everything is purely classical. And we immediately land just on those single scale integrals. And we already heard that now, of course, we can do the same methods as, for example, Mao and Michael discussed. So we can do all the IBP story and so on. I will show it actually afterwards to compute these type of integrals. At the end of the day, we still have to do this Fourier transform here, which is actually trivial because the answer is actually known for all M. This guy here only can compute, can only depend on Q squared. So the only thing he's going to get is this Fourier transform here. So at 3 p.m., we actually saw that we only land on a very small subset of integrals. So there was only one combination of square propagators that we needed, plus some combination of pluses and minuses here for the linear propagators. By now, we have essentially solved all the differential equations for these 20 like master integrals that we found either appearing in the just point-like action. We also looked at the tidal deformations. We looked at the dissipative and spin, and we have now control over all of these integrals. At 4 p.m., we found that for now, so for the point-like potential part, we only ever need 2 families of square propagators. And then, of course, again, together with some combination of I0 prescriptions for linear propagators. We expect that it doesn't scale much worse at higher orders. At the end of the day, it's really, those are the guys you have to compute. So you really need to do IVPs for just these few families. To give you some idea about numbers and generic strategies that we followed here. So once you've written down your integrand and you've done some tensor reduction, which is essentially trivial for our problem, it's just one single tensor here, you find something like that here. Okay, so we'll have some coefficient of some scalar integrals in the b mu direction. And for now, if we just care about conservative stuff, we can ignore all stuff, everything in the u directions. We found that we have around 70,000 integrals. And due to the epsilon poles, once we want to compare with Bonedal, we need to include higher epsilon corrections to the integrand. They come with some problem because essentially one would expect that you don't need them. If you really just want to get the physical answer at the end of the day, it seems like just unnecessary difficulty to aim for these epsilons here. So if you really would just compute the full delta P with distributive effects, those contributions won't be needed and they're completely unphysical. But for now, let's continue with them because then we can nicely compare to other approaches. The first thing we're going to do is to reduce this whole set of integrals to a smaller set of master integrals, my mi's here. For the problem at hand, there's around 160, and I can decompose each of these integrals as a superposition of these master integrals. For now, we actually found that this combination of light-red and fire6 works quite nicely. It's this light-red program that produces symmetries and finds some zero sectors for you, which is very nice. And then fire6 essentially does the hard work of finding these Dij coefficients here. Maybe there's also some details here that I can mention, that in principle, there's actually fewer master integrals because there's some identities relating some families and some subsectors that we decided to exclude for the reason that they introduce some nasty denominators. And once we go to the second step, once we do differential equations, you do not want to have these nasty denominators because they're making your life hard. So sometimes it's actually better to have a bigger set of master integrals if that helps you in getting nicer differential equations. Which brings me to the second step, because once you have written down your big set of master integrals, you can hit it with a derivative. The nice variable, as has been pointed out by Paramartinez, Ruf, and Seng, was that you should take derivatives with respect to this x variable that I introduced a little bit before. What then happens, of course, you're going to get a big system of first-order differential equations. The trick here is to bring it to a canonical or a pre-canonical form, as introduced by Hen, which essentially writes the system in the form here on the third line. The idea is that you pull out the epsilon dependence of your matrix that mixes all the integrals together. For actually most of our integrals, so what you do, you split all your integrals into different blocks. So you only look at blocks that are essentially interdependent, and you can solve block by block separately. What happens that for all except for one block, you can find the representation. So you can find the rotation here of your space, such that this AX matrix here vanishes. The single leftover block is exactly the guy that will give us elliptic integrals at the end of the day. Because it's known that the differential equation system for elliptic integrals cannot be brought into canonical form with just analytic transformations. It's just algebraic transformations. So what they're going to end up with is this guy here. It cannot be solved, so I will talk about elliptics a little bit afterwards. So once you're, so how you do it is that you essentially solve it order by order in epsilon, and you're going to get these FINs up to whatever desired order in epsilon that you need to plug into your integrand at the end of the day. One ingredient that is still missing are the boundary conditions. For us, essentially, we have to be careful, as also other people have been and we have heard in some talks before, that you need to be careful with these poles in x-1. If you just care about the potential regions, these poles for us is very simple. You simply look at the linear propagators and you can extract this power m here of the x-1 pole. And you will just be left with a set of static 3D integrals. You could now go ahead and compute all of these 160 static integrals. But we can do the same strategy as we did before, because we can once again do IBPs and symmetry relations on this big set of 3D static integrals. So maybe just to show you how we actually go to 3D is by using the delta functions here. So we're going to we choose a frame. Once you go to the static limit x goes to 1, and you're going to end up with a quite small family of static integrals. At the end of the day, if we again do IBPs, symmetries, we're ending up with only 7 independent master integrals on the boundary. And those were not too hard to compute. So 3 of them were very simple because they were just iterated bubble integrals. So you just open your Smirnov book, you look it up, and you plug it in. And the other 4 were actually coming in pairs of 2, where the linear combination of 2 always gave, again, an iterated bubble, and the difference between the 2 we actually had to compute. It turned out, though, it's not too hard. You can do a simple Schwinger-Feynman type parameterization. You plug it into Mathematica, and it will compute it for you. So at this stage, we can now assemble everything and plug it back into your expression for delta P. Once you do that, exactly, you just have to do the leftover Fourier transform, which is easy. You plug it in, and you can compute the u mu parts by using momentum conservation and dimensionless. And you're going to end up with your final result. Again, also here, I would like to comment on some interesting features. So first of all, up to 4 p.m. potential, we were able to really solve all of these integrals to all orders in D in the velocity, and we did not have to do any resummation. So even for the elliptics, we were able to do that. We can now essentially solve all of these integrals with enough. Exactly, it needs some computing power because they start to explode when you go to higher orders in epsilon. But essentially, we can compute them to any order in epsilon. For the elliptic block, the trick is that you bring it to this pre-canonical form. So you still have an epsilon to the 0 contribution to your differential equations. It turns out that you will find some nice small closed 3x3 blocks of, in the end, elliptic integrals. So what you can do there, then you rewrite this 3x3 first order differential system into one single third order differential equation. This equation can actually be solved by Mathematica, and you will find the quadratic expression in terms of complete elliptic functions, complete elliptic integrals, which are usually called k and d. What though happens if you go to off-diagonal blocks and even or higher orders iterations in epsilon, you will get iterated integrals over elliptic functions. So something like this guy here, which a priori seems very hard to compute. We are lucky because we found that the iterated integrals that actually appear in our delta P were very simple to compute, can essentially just be bootstrapped by simple ansatz of an expression itself in terms of complete elliptic integrals. So this turned out to be much simpler than expected at the end of the day. On the other hand, it also maybe tells us that at higher orders, there's a big chance that we will end up with, let's say, true iterated elliptic integrals, which will be much harder to compute than the guys that we found here. Another point is that we have, again, due to our splitting into potential radiation, we have this annoying epsilon pole. Due to that, as I said, we had to expand our integral also to order epsilon 1. And that was exactly essentially needed to match to the result of Bernadette. But it seems like a little bit of an overkill to me to actually do that. It should not be necessary to compute these contributions. At the end of the day, we know that there will be tail contributions that will kill the pole, and everything that comes with it is just unphysical. A last point that is interesting that we have not fully explored yet, but that's maybe something for the future, is that we can learn about the boundary conditions from certain constraints, or for example, from the Schwarzschild contributions. We know the Schwarzschild result, the Schwarzschild terms are the ones that are new to the 0 to all orders. And we were actually able to at least cross-check that our boundary conditions are correct, or at least consistent to some degree, by just looking at these contributions and looking at it. So it's not that the data is coming from the Schwarzschild contributions together with the three-dimensional IBPs. They really constrain a lot, but at the end of the day you just have 7 boundary conditions that you need to compute. It's just a small set that really just shuffled in through the IBPs, and they're coming somehow mixed back up and give your Schwarzschild contributions. Even further on, actually, another point where you could use that is if you really compute the full result. You know it has to be physical, so you know that all the epsilon poles have to cancel. But you already saw that to kill, there was a 1 over epsilon squared pole. To kill that guy would also have given us one more constraint on our boundary conditions if you would not have computed them already. This is very nice, and maybe there's something in the future. At least it's a good consistency constraint, but maybe it also helps us to at least partially bootstrap some of the boundary conditions. All right. Okay. Are there any questions until now?
Maybe I can ask, Gregor.
Yeah, sure.
So these iterated elliptic integrals, what do you mean by bootstrap on the right-hand side?
So by bootstrap, I mean we simply made an ansatz in a quadratic expression of k and d.
And how do you fix the ansatz?
You take a derivative, and of course you should land on this integrand here.
I see. Thanks.
So the nice thing is that, well, what happens that you always get this nice denominator here, which is exactly, if you take derivatives of k's and d's, you're exactly going to get this denominator back here. So that's how we, since we didn't realize as well that that's what we should do, because we saw that it looks too nice to be exactly something complicated. It doesn't work for all. So I think, so we looked at it. We had, in principle, in our differential equations, we had around 100 combination of elliptics appearing, of iterated elliptics appearing, and around 50% of them we were able to bootstrap with a simple ansatz like that. At the end of the day, there was actually only one that appeared, one combination of elliptics that appeared, iterated elliptics that appeared up to the finite terms in epsilon.
By the way, just a technical question. When you write k open a parenthesis 1 minus x squared square, this is the square of k evaluated at the argument 1 minus x squared?
Yeah, so that's the mathematical convention. There's different conventions floating around. Yes, exactly. So sometimes it gets defined with a square root in there. Yeah, I didn't show it here, but you need to do some transformation to land on the elliptic integrals that Bernadal gave in their paper. So first you need to go to gamma space, but that's not sufficient. You also need to do some transformation on them. But you hopefully be able to present that very soon in our paper. It's not too hard, but it's also not trivial. All right. Okay. So now let's finally come to the B2B dictionary. So this is the second part of the story, where we try to relate all kinds of observable once you have computed them in whatever way we like. So for me, some of the basic part is the relation between orbital elements of these two problems. On one hand, we have the bound problem of two black holes or neutron star black hole, whatever, orbiting each other. And on the other hand, two particles, two black holes, whatever, scattering. The nice relation is given by the radii. So for the scattering problem, we have one interesting quantity, which is this minimal distance between the black holes when they pass each other. Formally, it's defined as the positive real root of the radial momentum, which can be extracted, let's say, once, okay, maybe just say for just this is only for now working for conservative motion in this setup here, can be obtained from the momentum on the trajectory, which is easily found from a Hamiltonian by inverting it. All right, so we need to find positive real roots of this quantity here. We do that in the PM expansion. So essentially, this p squared will be a polynomial in g over r to n to some power, and we can just brute force essentially solve it. So for the scattering, exactly, we'll have positive binding energy. There is only one single positive root, and that's the true minimal distance. if you go to bound case, you have negative bounding energy, and you will have to find two different radii. So you will have the closest distance, the r minus, and you will have the biggest distance between the two bodies, the r plus. And those again are defined as the two positive real roots of the same polynomial. But if you see here I've written in terms of the impact parameter b, but for bound orbits, b doesn't make too much sense because formally it's going to be a purely complex number because you will have p squared is negative. So it's better, somewhat more intuitive to write it in terms of j, of the angular momentum. What you have shown in these papers here with Rafael Porto was that we can relate the r min of the scattering problem to the r minus and r plus of the bound problem by these relations down here. So you have to do r min and r minus are simply related by an analytic continuation. So really you need to write b as a function of j. This b is now going to be complex, and you will find this relation here. For r plus, you simply need to swap the sign of j, and that's what you have. Okay. This works very nicely, non-perturbatively, as well as in the PM expansion. So we essentially give relations like this guy here to all orders. The trick here was to use this Firsoff relation, which I will talk about actually in the last part of my talk. So once you have computed the scattering angle, which we did, right, to fourth order, you can plug it in here, and in principle you can even compute this r min. You can continue it, and you get r minus r plus. But in principle, you don't even need to do that because there's some much nicer story behind it. So if you do some classical mechanics, you're going to write down an expression for the scattering angle in terms of the momentum along the trajectory, and you'll find an integral like that. So you're going to integrate from exactly this radius, this minimal distance to infinity in R. Okay, there's a very similar quantity if you look at the bound problem, which is the periodicity of the bonds. For that, you're going to have to do a very similar integral, but you won't have to integrate between, well, something in infinity, but between the two radii, right? Because that's what you do. You can also imagine some of that this geometry is essentially very similar for a scattering case. You're simply going to close your orbit at infinity. You're going to go back. So essentially, you can take some Riemann sphere, put your point infinity there, and you're also going to get a closed orbit. And that's exactly what happens. Because by our identity above, between r min and r minus, and r min and r plus, you can now do the detour around infinity, and you find this nice relation here, which simply tells you that the periodicity of the bonds can be found by an analytic continuation of chi j plus chi of minus j. Again, of course, you have to continue as well in the energy, so go to negative bounding energy as well as the angular momentum. You can now play the same story with other observables as well. We also heard from Rafael about some dissipative objects like the energy loss or the loss in angular momentum, as well as from Bini and Tamur. The quantity I think that's most interesting, or at least to be the central object, is the radial action. For us, how we obtained it first was by integrating up the scattering angle, or rather actually on the bound case for the periodicity of the bonds. In principle, but you could also play the same game. So again, you write down the defining integral for these quantities. You're going to integrate between r min and infinity, respectively from r minus r plus. And now you're going to get a very similar identity. But you have to be careful now that there's a minus sign inside. Maybe something I should have said, that this all crucially depends on the j square here. This only works because our integrand is invariant under flipping j, goes to minus j. Which brings me essentially to the last point here, is that you can do the same also for aligned spins. So aligned spin, I mean that you have two, let's say, black holes with spin aligned the same direction, which are still going to orbit in the same plane. So essentially the geometry is unchanged, except that you now have a different total angular momentum, which is put together from the angular piece and the spin piece. And you also showed in the second paper in the series that the very same relation between periodicity of bonds and scattering angle holds. And of course, this can now be again uplifted to the radial action and any other quantity that you're interested in. We checked it for Pn and Pm. And also here, again, what is important is that you have the relation between J and minus J. This is somehow, at least at this point, my understanding that this goes very nicely together with our construction as well as the amplitude construction, where we somehow by definition land in this quasi-isotropic gauge, where this is always true. Okay, I'm almost out of time, but for the last couple of minutes, I also would like to discuss something that's very closely related to all of this, which is this spheres of identity. So the magic here is somehow that it allows us to extract Pn information from Pn. I want to do a very simple example to showcase you what's happened here. We just saw before that we can relate the peri-astronaut bonds to the scattering angle. Okay, so in a Pm expanded way, you will write down an identity like that. If you now assume, let's say that we do not know anything about the 4 Pm scattering, so we only know chi1 up to chi3. You would now guess, well, we don't know anything about chi4, right? Because we would need about delta phi 4, because we don't know anything about chi4. But that's actually wrong, because, well, the information should be there. The delta J4, for example, contains 2 and 1 Pn information, which we somehow should be able to extract from our Pm results. And the matching is all coming from this Firsoff formula. So the idea is that here's written down, so that's the Firsoff identity here, this guy here, that he relates the momentum along the trajectory to the scattering angle. Note here that, of course, we have the usual identity between a scattering angle and the momentum along the trajectory, but there's this annoying Rmin in there. Yes, we have shown how you can express in terms of chi, and you could, in principle, invert it directly, but it turns out it's very hard because you will have to resum some infinite tower of contributions to do that. But it's much easier if you look at this equation here, which you can really solve order by order in powers of g. So let's say exactly do an expansion again, g over b for a scattering angle, g over r for my momentum, and we have written down all these relations here. Okay, you can invert it. So essentially what it means that each order in chi can be written in terms of each order of the p. So I call this f coefficients here, which is actually more or less the same as these p coefficients that have been in the original 3 Pm paper by Bernadette. So now we can use that. Because, so you have the relation that the peri-astronaut bonds is related to the scattering angle. Okay, I'm just gonna change from J space to B space. And finally, I'm gonna write it in terms of this F by using these Firsoff relations up here. Okay. The nice thing is now that we know F1, F3, F2 by going back to the angle because we computed K1, K2, and K3, right? So we can plug those guys back in. We don't know F4, so we're gonna ignore it. And the magic here is that even you think, well, we just went back to the original one, so we went in circles. We actually did not, because like that, we produced the 1 and Pn information. In this example, at g to the minus 4. And for conservative effects, this actually always works to all orders and perfectly reproduced everything that we could check until now. All right. So since my time is more or less over,
yeah, five or so minutes. Good.
Okay, good, because I'm almost there. Good. So maybe about that. There's exactly, if I have some time, I can also talk about generalizations. Since we in our newest results, we saw that we now going to get poles, we're going to get logs. The whole framework can actually be extended, and it's quite trivial to do that. So it took us, I don't know, half an hour to work it out. So you're going to put this out to the epsilon terms in the momentum. You're going to put b to the epsilon terms to the chi. Of course, you might want to exclude them. Also put out some other stuff. Just ignore it for simplicity now. And you're going to write down very similar expressions that relate the Fn coefficients to the chi b coefficients. They're essentially just going to be addressed by some epsilons in the scams that we had before. You're going to get some epsilon also in this g coefficient. Doesn't really know what it is, but it's just a purely combinatorial combination that you put there, put it into Mathematica, you compute it. So explicitly, you'll find something like that. And the important guy for the computation at hand was this guy here, this chi b4 coefficient, because that's the one that was needed, that we can actually fit our chi result, or our result for chi before, to the C4 coefficient in the Hamiltonian. So there in our first paper, we gave a relation how we can go from the momentum on the trajectory to the coefficients of the Hamiltonian potential, the effective potential in the two-body problem, by simple formula. And we've actually checked that we reproduce the C4 coefficient in the paper by Bernadal obtained from the scattering angle. And this guy here was very crucial to also get the epsilon corrections and the logs correct. All right. So at this point, I think I can start to conclude. For me, important was here that the Post-Minkowskian EFT, together with this boundary-to-bound dictionary, really seems to give us everything that we need. Of course, we're missing some final pieces if you talk about spin, or if you talk about dissipative effects that we do not 100% understand yet. They need to be a little more careful, they need to work out. Nevertheless, it's an almost complete framework to study the whole classical gravitational two-body dynamics if we talk about scattering or elliptic motions. So everything is in there, and it's very efficient. Also, it nicely goes hand in hand with all the modern integration techniques. We get a very small subset, very few families of integrals. Everything that we have found so far can be handled by these modern techniques. We don't need any resummation anymore. Everything is handled by differential equations, IBPs, computing boundary conditions. Yes. Finally, exactly as I just showed you, we have now obtained the contribution of 4 p.m. We hope to soon extend that to the tail and hopefully also the full dissipative order. Maybe one point that we might also discuss maybe in the discussion afterwards is this epsilon poles. It really seems like we're just creating some artificial problems here by splitting into potential and radiation. I agree, it's computationally, there are reasons to do that, to do the split. But at the end of the day, we really should consider if you're not, at least at some point, doing too much work by exactly keeping unphysical terms that we know that have to cancel out. So why we should even compute them? Why should we bother? So maybe it's about how we find out what's the best setup, how can we ignore them as soon as possible, how can we really target the pieces that we need. And finally, I hope I brought some light on this Firstov's formula that we understand better and better. That essentially gives us two things. It relates the scattering angle to the momentum on the trajectory in a very nice way. And it also allows us to understand the relation between Pn and Pm. In the future is bright, I would say, because we have not reached any tools capacity at the moment. So there's a lot of space how we can expand. 4 p.m. was not as hard as we expected. It took us some time, that's normal. There's bugs, there's tricky things that we need to learn. We learn now, we know better, and we're gonna get better. Our first priority will definitely be to complete the 4 p.m. We have a clear path to compute the tail effects, but also dissipative effects. What's maybe important to understand better will be these iterated elliptic integrals. It seems to be that there's a very similar structure as the polylogs that appear there, or hyperpolylogarithms. So some of them can be easily iterated, so logs give you logs again, and sometimes you're unlucky and don't get polylogs and higher stuff. Finally, my last point maybe is that we should also further study this B2B map. For arbitrary spin, there's again, the geometry needs to be understood a little bit better, but maybe there's a similar effect that can be done then. And as Rafael already has talked about a little bit, also dissipative effects will need to have been fully understood. Okay, with that, I'm gonna stop and open for questions.
Great, thank you, Gregor, that's very nice. And let me check here for questions. Raise your hand or just open your mic and talk. I see a lot of clapping, I'm guessing, right? Clapping, it means good, no question, right?
Everything was clear. Good.
Oh, I see a hand. I see a hand. I see a hand. I see one hand. So whoever you are, I don't see you. Just talk.
It's me.
Okay.
Julio,
So
of course.
maybe-
Go ahead.
maybe we should delay this for the discussion, but I wonder these comments about the scheme-dependent pieces that you're making of the epsilon over epsilon. So when you compute an amplitude, there's also these pieces. Whenever you have infrared divergences or UV divergences, there's finite parts of the amplitude which are scheme-dependent.
Yes.
And in general, it's a very complicated problem to see ahead which finite pieces are the ones that don't belong and the ones that belong that will cancel in a cross section. So is there any reason why in this case you think that the situation is better and you can ahead of time target them and just say all these scheme dependence and I can just ignore it?
We hope that we can do it. So it's not as simple as we hoped it would be. So it doesn't just work by exactly throwing away epsilon pc in the integrand. We check that. It does not give the correct contribution. So also for us, it's not trivial, indeed. But for me, what I hope here is that if we really target the full answer at once, there should physically be no reason why you would, so at least for us, we should be able to throw away epsilon pieces in the integrand in the first place. After, you still have to be careful in the integrals that you cancel them properly. They will still be, you still will have to carry along this epsilons, I agree, but at least from the integrand side, they should not be necessary.
So just to see if I understand, are you just saying that if we compute full soft, there's no 1 over epsilon and then there's no scheme dependence? Or are you saying something about being more intelligent when you split into potential radiation?
No.
Okay.
Nothing
If
clever
you do
here.
the full thing, they shouldn't be scheme dependent. Okay.
So, but we do know what the 1 over epsilon pole should look like because we have the universal part of the tail. So in this special case, we actually know what the unphysical pieces are, but that's very unique of this case. In general, so when we started doing this, I told them, do not include the other epsilon test. We're doing the full soft region, it's all finite. We don't care about the pole. However, when we start comparing, we're not getting the same answer. And then what the heck is going on? And then we start adding the other epsilon integrands, and then we see all these extra pieces coming out, but they're completely unphysical. You should not have included them in any case, right? So now the question is, can you do that at the level of the integrand and so on? We honestly don't know how to do it. But in this case, because we know the tail will cancel with the other epsilon corrections of the flux, also the potential, we kind of know what we need to subtract. But this is very special.
Sure, I mean, I agree that the scheme dependence will cancel when you add everything, but I thought you were trying to make a different point, which generally is very hard to, whenever you have scheme dependence, to know which part is the scheme dependence.
No, exactly. In general, we cannot do that. I agree. Yes, it's the same problem as you have. Yes.
Well, except in this case, you know that the tail is universal, right? So you know.
Yeah, but that's okay. That's for now. Yes, for this specific
is a very special
contribution.
Case. In general, I agree with you. In fact, we try, as you will see, maybe we discuss this later, where it goes. You'll see where it goes. A few places where you can see it happening.
Yeah, I have a similar question. Like, if I think about the all plus amplitude in QCD, I mean, there is crucial that I keep that I keep mu terms in the integrand, otherwise I get 0. So, I mean, there is something. I mean, sometimes there is something physical in these pieces. No, I mean, so
absolutely.
Okay.
So you have to. I mean, so you can't just like toss every piece that you would vanish in 4 dimensions from an integrand.
No, absolutely not.
So
yeah, that's not what we're saying. It's just that right now, at least for this problem here, we know we're computing too much. So as I'm saying, it needs to be understood what we can throw away and what we cannot throw away. I completely agree with you. Yes, there are problems and subtleties there.
In the discussion. This is a classical calculation, number 1. Nothing runs. Well, you can make it run, but nothing really runs, right? And this is no log of R. There is no log of R, there is no log of B. All that is fictitious. The pole is fictitious, the log is fictitious. You'll see what is the real physical information.
Sir, I think I'm a little bit confused. Why do you say the logs are fictitious? At least the log V will survive in the final answer.
The log mu is gone in the final answer, and the log of B is gone as well.
Yeah, but the log V will survive. Right?
The log of velocity, which is energy.
Yeah, that one is a different contribution. It's a different story. Yeah.
And that's the one we should target, not the log of R, not the log of B, not the mu, not the epsilon, the log of energy. That's the only thing that we care. And we actually know it's universal.
Yeah.
So that's what matters.
We already know where it's coming from. If you look at if you look at the soft boundary conditions, the log is sitting in there. There's a x minus 1 to the epsilon in there.
It's actually very pretty. Once you add the soft boundary conditions, we know where this log is coming from, and that's the only thing that we should be targeting.
But I think what's even more tricky is the finite part that's under the log, because the logs, as usual, are because they're related to divergence and they're easier to target. But it's actually the finite part.
Yeah, but in this case, it's not. Actually, if you guessed through the divergence what the coefficient of the log should be, you're off by a factor of 2. You get it wrong.
No, I understand that factor of 2, in fact, because I think you refer to like the log we get from potential versus like the final log.
Yes, no, the final log is the one that you should target, and also the final pieces. And those are the ones that we truly need to calculate. I agree with you. We still haven't fully added the soft boundary conditions, right?
But we understand why there's a factor of 2 between the log in potential region versus the one in radiation.
You said you understand?
Yeah.
Okay.
Yeah, we can talk about this more.
No, I know why. That's what I pointed it out.
Maybe I can, okay. We can, of course, talk about this in the discussion, but I just want to know, maybe you can say more about the B2B map for the dissipative sector.
So, okay, for example, some guys that is already understood are the energy loss and the loss of angular momentum.
It should be plus J, by the way. It should be plus, no minus, because this
I screwed up the sign. I copied from your slides.
No, it's a plus. I put plus in my slide.
Okay, sorry. Yeah. So exactly. So those can be derived essentially in the very same way. So you can, I mean, Raphael did it in his talk. Essentially, you can write down these integrals. The only flip you're going to do is, again, you integrate between R plus and R minus, or R minus to infinity. So, okay, what we tried to understand actually was from the PN point of view. So if you look at the paper by Bini and Tamur and company, so they split it into different parts. So I'm not sure if you've seen this in this paper, they essentially integrate the Hamiltonian, and you get this W. So what's for us essentially the radial action, hyperbolic radial action. They split into local and non-local. So the local piece is completely understood, works out here. But even part of this non-local piece actually goes through here everywhere. So they call it W1 and W2. The difference between these two is that one of these non-local pieces has a log in there, this log U, as they call it. And that guy is the tricky part. All the rest, the other guy, it goes again through this continuation here. So what it seems like, if we can really extract the coefficient of this log U, we will just have to redo the integrals. Instead of integrating from, well, in the trajectory case, to integrate between the bound orbits, we can just redo this well, extract it from the scattering result and add it back in the elliptic result. But for that, we have to compute the flux and really redo this log integral with the flux.
What's log U here?
So U is 1 over R, I think. So it's the...
Oh, this is omega.
I see.
Oh, the omega, exactly, the energy integral.
Yeah, there's a flux times log of omega, which is the non-local part. I can show right now that goes the same way that Gregor explained, but in the large eccentricity limit, which is unphysical for the non-local part if you're gonna go near a circular. What we have to do right now, and that's the only way I have found how to do this, is what Gregor just said. Take it out, because we know how to calculate it, and put it back on, but in an orbit. Because the flux itself is the same function, more or less, right? So this is the only way we found right now how to deal with the non-local piece for quasi-circular orbit. If you just want to say large eccentricity, then everything goes. And it's the same orbital elements again, because remember, this non-local piece is evaluated on the classical conservative trajectory. And therefore, I can use the same analytic continuation. Every time I do that, the orbital elements do the magic. But it's always in the large J limit, the same way that the flux of 1 over J cube only gives you that piece of the large J limit. You're missing the 1 for the circular quadrupole formula. The same will happen here, and we're gonna get it completely wrong. So we need to recapture that 1 of the flux, and we can do it, but right now we don't have a very efficient way to do it, let's say. We have to remove it and put it back, which is kind of annoying.
Can I ask a slightly different question? So I'm wondering, why do you focus on the impulse or the angle rather than on the radial action directly? Presumably you can also compute it, but you're adding like extra numerators. You have to differentiate under the integral sign. I mean, there's some extra work involved. Is there any advantage to look at the angle rather than directly compute the radial action in your case?
I agree with you that it might be nicer, but honestly, I mean, that's a story, for example, Plevka, Steinhoff, and Mogul that directly would target something like the radial action. But there's some problems there that we don't know exactly how we exactly have to do it. And there seems to be a problem with the boundary conditions there. So Feynman versus retarded again. That, yeah.
Sorry, but for conservative, like forget about dissipative for now. I'm just wondering, for conservative, it seems to me that two nodes in this, like node graph can be removed and just focus on the radial action, and then all the observables.
Yeah, the problem, it doesn't work at 3 p.m. There's some problem there. We would like to do it that way, but
no, the question that Julio asking is a little different. We can perturbatively at each order iterate the previous guy and go straight to the radial action. That we could do. But if you already have the code for the impulse, and it's not that much more work, to be honest, you can just iterate there.
Okay, so it's just inertia, but in principle, there's an extra derivative that you take at some point, and you could not take it. And then you would have simpler
but that extra
numerators.
derivative is really just a Fourier transform, so it doesn't really do much.
Exactly.
Yeah, well, but it's an extra numerator, right? So,
yeah, but compared to what you have to do, that's enough. But I agree with you. In fact, the tail piece, we will probably do that way. It's directly to the radial action.